Good afternoon. I'm Friedemann Freund. I'm here at NASA Ames. And I wanted to tell you something I've been working on for quite a number of years, namely, where does the water hide? And if I can have the next slide, is there a... Yeah, I'm not talking about any of the water that has attracted so much attention as the one that is tucked away in the permanently shaded craters. But I'm talking about the rest of the moon, which looks so very barren. And since the Apollo time and the laboratory analysis of samples that were brought back, that there is precious little OH in the minerals, with very few exceptions. And even when they looked for some of the amount of hydrogen, not only OH, but hydrogen, they found that actually it really looks very depleted. So the next slide shows that everybody more or less agrees that the moon formed out of ejecta that were circling the Earth, and that during this time of the initially hot magma that was injected during a large impact, there was some amount of degassing. But it is totally unreasonable and inconsistent with anything we know from laboratory experience. We cannot degas a magma once it has dissolved traces of water. And to demonstrate this, just the next slide shows you if you make a phase diagram between two components, water and a nominally anhydrous mineral, if you magnify the composition near the mineral composition, the mineral is a solid solution. It incorporates the water that is in the magma when the crystal could be feldspar, could be pyroxene, could be olivine, could be anything that is nominally anhydrous. It will incorporate water in form of OH in the crystal structure when they crystallize at high temperature. And at the high temperature, the amount of water is highest, and then as you cool down, it forms a solid solution of a compound AO with some of the hydroxyl. And in order to incorporate the hydroxyl, you would, for instance, leave out cations in order to achieve balance. And therefore, then when it cools down this way. Sooner or later, there will be kinetically inhibited freezing, and you enter in a regime that we know as supersaturated solid solution. And what you would actually then pick up or see on the surface of the moon or on the Earth is a solid solution that you would actually expect to have hydroxyl. And even if the degassing, the next slide, is more pronounced, you may go a little bit further down this aisle here, but you can never reach zero. So there will always be some residual OH should be present in these minerals. The next slide then goes the basic, very fundamental reaction. You take a tectosilicate, let's say a feldspar, you react it with water, and you break the SiO bond, and you form a OH pair by breaking this bond. And this is not possible to degas. There must therefore be some residual. But then the question arises, why don't they, or why is the amount of residual OH in much of the lunar rocks so small? Well, there is one reaction, the next slide, which actually we discovered some time ago. Oops, where's here, where you have the hydroxyl pair, that during cooling, and we know more or less the temperature interval in which this happens, around between the upper limit 600 degrees, lower limit about 400 degrees, there is a redox reaction. Electrons are being donated by the oxygen to the proton. Both sides, the proton get together, form a molecular hydrogen, and the oxygen becomes oxidized to the peroxy state from the formal valence state minus to the valence state -1, forming a peroxy bond. This peroxy bond is a very short bond. It's only 1.5 angstrom long, The volume, if you draw a box around here, the volume of this box is barely that of one oxygen. Now, the next slide shows that hydrogen is diffusively mobile and could leave the place where this reaction has taken place, particularly if it has lots of time and additional activation. And if this happens, you would actually reach a situation which is quite interesting, that the former water content here is maintained in the solid in the kind of a memory for these peroxy defects. And therefore, these peroxy defects now represent a memory of the water that was once incorporated in this mineral structure. Next slide, please. Shows now that if you draw it in a phase diagram, you have a region where this redox conversion takes place around 500 degrees. Below this temperature, a fair fraction, probably in our laboratory experiment, somewhere between 90 and 99% of the hydroxyl disappear, for instance, from the infrared spectrum, because they have converted into molecular hydrogen that at the beginning sits on interstitial sites, and down here in the solid supersaturated as well in the normal solid solution, you would have a modified chemical structure which would have to incorporate hydrogen. And the oxygen now is not all oxygen are valence 2-, a certain fraction, namely 2 delta of this, would be in the valence 1-. Next slide, and shows if the hydrogen goes away, you end up with a mineral composition which has no longer any trace of hydrogen, and it is a non-stoichiometric compound. Most of the basic work was done with magnesium oxide as a model, but then it was confirmed for both olivine and feldspars and for a number of other compounds, minerals. You have a composition that is an excess of cation vacancies compensated by changes of valency in the oxygen sublattice. The next slide shows what you can approximate this. You can say if delta is really small, you can rewrite this approximately that you actually have a mineral with excess oxygen. Now this is a metastable state. It forms only in a temperature regime where thermodynamic equilibrium can no longer be achieved, but this is a composition that we would have to take into account. So for lunar rocks, or the moon in general, it would therefore be wrong, I should put this in quotation marks, to look for OH-. It would be wrong to even look for hydrogen. If you want to learn something, how much water was in there, we would have to look for peroxy, for these point defects. And the next slide just shows you a little bit whining from my side, because I've been working on this for a good 35 years, and we have essentially thrown every technique that is available on the books to study these peroxy defects, first in magnesium oxide, and then in minerals and in gases. And we were able to show consistently that in magnesium oxide, the stoichiometry 1-to-1 is not followed. It deviates from it because of this formation, and then it was substantiated and broadly applied to earth minerals in a sequence of papers that appeared until about 5 or 10 years ago. Now, today I would like to propose that this should also be given consideration for lunar rocks and lunar samples. The next slide, please, is if we have testable in the laboratory, as I said, we have done essentially all measurements that were possible to understand the behavior of these peroxy. We used in particular dielectric polarization measurement, but we took Raman spectroscopy, muon spectroscopy, you call it electrical conductivity, all kinds of techniques that are available in order to characterize what it means if there is valence changes in the oxygen sublattice. And for the moon, remote sensing, one could possibly look for UV induced surface charging. I don't have the time to talk about this so much. Look for some modified ways that would come out with this surface charging due to the dust levitation, electrostatic dust levitation. Look also for water emitted at the morning terminator, because when the UV light hits the surface, there are certain chemical reactions to be expected on the basis of the oxygen being in valence -1. Look for narrow infrared emission that we have shown to exist when these charge carriers recombine. There is a very characteristic infrared emission in around 9.7 micron and longer wavelengths. And then maybe even we have seen changes in radar reflectivity that result from the activation of these electronic charge carriers that are characteristic of the oxygen signal minus. So the next slide just is the end. And thank you. I just wanted to solid a lot of questions, because this is an interesting and potentially quite important aspect that should be taken into consideration. Thank you.
Yes, I'd like to point out to you that there's a paper in Nature Geoscience that's coming out now, and it's based upon FTIR and SIMS work on lunar glasses. And we've shown conclusively that it's OH that's in there. So OH is present in various degrees from a few parts per million up to almost 1,000 parts per million in agglutinated glass. And so I think that although you have a good story to make here, I think the fact is that there's a little bit difference between your starting material and the lunar soil itself. Yeah. I'd like to emphasize that.
Yes, thank you. I agree fully with you, because the driving force for this redox reaction conversion is actually highest if you have a dense mineral structure. If you have a mineral structure that is rather open, like quartz or feldspars or glasses, then the conversion degree of conversion is much less. However, we do find, if we then look for peroxy, for instance, in fused silica, we do see evidence for the peroxy defect. And the peroxy defect has been known for 20 years to be one of the main defects that creates headaches for the optical fiber people, because it is involved in darkening of the optical fiber if you make long optical fiber transmission lines. So I fully agree with you that glass is not a very strong component, but minerals are.
We find this in silicate minerals as well.
Yes.
We also find this primarily in apatite, this hydroxy fluorochlorapatite. Yes. And we find water in there, or OH in there,
yeah,
which we've identified as OH per FTIR.
Yes, but apatite, of course, is a structure that has a crystallographic place for OH to be. It's not a nominally anhydrous. That's, I agree.
Running a little long. One other quick question. Sounds like a good debate to have over a beer, then.
Fine.
So some of the things that we could observe that you had recommended using remote sensing data, I think some of them have been done. And I guess my question is, how would we know whether we're looking at water using those techniques versus peroxy?
Well, if the peroxy derives from water, which I think it does, it may also derive from other gases, then you essentially, the presence of peroxy would tell you something about a former presence of solute water.
Fred, we're going to have to move on. I'm sorry.
Thank you.
Thanks again.